Hello and welcome back to the Survey of Plasma Physics course. Today we are going to talk a little bit more about inertial confinement fusion, and if all goes well, we'll finish today and move on to different topics in the next lecture. I'm going to add one additional piece of information to what we have already been discussing about the shell design, where instead of imploding symmetrical homogeneous target, we implode a target which has a specific material that is ablated from the surface of the target, and the rest of the target is then compressed, the part that contains the fuel. In fact, it's even a little bit more complicated than that, but let's leave it at that for our purposes. And one thing that I've not yet emphasized is that the final pressure of the fuel, again, I'm not giving you any details. It's once more not a complicated calculation, but we don't have time to do even the easy ones. Oops, that's horrible. Let me try again. We call it P sub F. It's going to be equal to P sub A, the pressure, the ablation pressure. But what is important is that it's proportional to R0, the initial size of the target, divided by delta R, the thickness of the shell. So once again, we see that in this type of design, high aspect ratio, where this ratio, the ratio in this expression, R0 divided by delta R, is large, we get a larger final pressure. We are trying to compress the fuel and get it to high pressure, so that's a good thing. But again, we will not discuss instabilities, but that's what's really limiting the aspect ratio. Now, we have said that we have hopefully a reasonable picture of how we're trying to compress our fuel. Now, what happens is that as we try to compress our fuel, we form shock waves. And the reason why that happens is that a wave travels faster in higher density material. The shell is, or foil, or the material we're ablating is more dense than the fuel. And also the sound speed, let me start in general. Okay, don't want to get into too much detail about this part, but and we can assume that the initial pressure wave is just a pressure wave, that is a sound wave. And therefore it travels with the speed of sound, but the speed of sound goes up as the pressure goes up. And in practice, what happens is that high pressure disturbances catch up with low pressure disturbances. And therefore, the pressure piles up and the compression wave steepens into a shock front. That's the very dirty, hand-wavy explanation of why we end up with a shock. I'm not going to get much into shock physics, but I'm going to point out just a couple of things. We did see, let me put it back, in lecture 16, the Rankin-Ogonyo conditions that the maximum compression we can have with a shock is a factor of 4 in the density. Rho1 is after the compression, Rho0 is before the compression. However, and I did not really elaborate much on that expression, the fluid dynamics involved. However, that is for a plane shock, that is for a slab solution. In a sphere, something similar happens, but similar but not identical, and there is at least one important difference. And let's see if I can make a little sketch. Here we have shock wave that comes in, say it goes through my material, and then it keeps going. The red is a shock wave before it meets the material, green is after it meets the material. Now, let's suppose we have a spherical target. Wow, okay. We did not understand each other here. Try again. Okay, spherical target. We have a shock wave coming in. Let's assume there is some thickness, or even for this will work here for a homogeneous target actually. The shock wave gets into the material, keeps traveling. What happens when the shock wave gets to the center? Well, if we're compressing uniformly, there is a shock wave coming from every direction. It's symmetrical, it has spherical symmetry. That means that the shock wave will meet itself at r equals 0, coming from the opposite side. And then it will be reflected, and then what I'm going to have is another shock that travels in the opposite direction, and that's going to give me more compression. In fact, what more detailed, well, a detailed calculation shows is that there is a considerable difference between, in this case, the planar shock, and in this case, the spherical shock. pause and try to guess what the number is going to be. It's actually almost 10 times as much. Well, 8 point, you do the math, but it's a factor of 33 instead of a factor of 4. This is a combination of a number of, of things. The reflection and recompression by the traveling shock is part of it, but that's not all there is to it. An additional element is the spherical convergence of the fuel. As the fuel starts moving in the radial direction, its density will increase. While if I get my slab in the picture on top of the page moving to the right, it will just move to the right. But the constraint of spherical geometry and spherical symmetry means that as my target moves in the radial direction towards smaller radii, it needs to compress. I have the same amount of mass that's going to occupy a smaller volume. So that's the other element that comes into play. Okay, then things actually don't ever work as well as we would like. You're not going to see, sorry, such such a nice result. This is the ideal case. So it's again the limit. The limit case. One catch is that the the amount of energy that's required to get a good spherical compression with a single shock is actually very high. And we don't have time to get into it. What will be really more efficient in terms of how much energy do I need to compress my fuel is an isentropic compression. Is an isentropic compression requires less energy to well, compress the fuel. But I just argued, not in an outrageous amount of detail, that if you start compressing the fuel, the process we have described, you will end up with a shock. So the approach that is used in ICF is to try to have a sequence of shocks that are going to be much closer than a single shock to an actual isentropic compression. Now, let me try to make a little sketch. Let's see if I can clarify what I mean. Let's see. No, let me start with blue. Let's say we have the specific volume. It's the inverse of the density on the horizontal axis and the pressure on the vertical axis. And then let's say we want to compress from pressure 1 here. Well, didn't go as intended to pressure 2 down here. But I just wanted to make a thick line, not an actual rectangle. Okay. All right. Let me call these P1 and P2. And let's say that this is my starting point, and this is my end point. If I can have an adiabatic compression, that's what I will do. While a shock will give me a compression that looks like this. It doesn't come back. But point being that that area is going to be bigger, the area under the curve, and that that means that this process requires more energy. However, one thing that can be done is to have multiple shocks and have a curve like something like this. And what the result of having multiple shocks will be is that we're going to be that much closer to an adiabat. Let me clarify, or let me tag these things. Let's see. Take compression, thread, single shock, we make it green. And the one in the middle is multiple shocks. Okay, if you do that, there is one more thing you have to concern yourself with, and that is, are the shocks going to meet each other, fasten them in sequence, or not? Well, yes, regardless. I mean, it's a spherical target, so at some point, the first shock will reach the center, then we'll have to come back, and maybe the second shock on its way back. Or I can design the experiment in such a way that the shocks meet all in the center. And that's what I would want to do. And the reason is that where the shocks meet, I'm actually going to heat the plasma. I'm going to put in temperature, not just compression. And I want the fuel to get hot in the center of the plasma. And I don't want to get the center of the plasma hot before I compress it. Because if I do that, it's going to take more work to do the compression. So part of the careful design of the shocks in ICF is aimed at having the shocks meet in the center of the target. That's not for getting extra compression, that's for energy deposition, getting the temperature up in the center after and not before we have compressed the plasma. There is some well, there will be something more to say about Fermi degeneracy, but I'm not going to get into that. I think I will only briefly give you an idea of how you go calculate the burn fraction. We have already seen an expression for that. If you remember that an expression dependent on rho r. And I think it may be interesting to see where that expression comes from or how you can figure it out. The fractional burn, by definition, is the fraction of the fuel that actually does nuclear fusion. Put a square around that too, maybe in a different color. Here. Now, starting point is the nuclear fusion reaction rate that is going to consume my fuel. So that's going to give me a derivative of the density of the fuel with respect to time. That's going to be equal to the reaction rate. That's with the opposite sign, with the negative sign. And that reaction rate is going to be given by the density of the deuterium times the density of the tritium times the distribution function average, the fusion cross section. And if as it's usually the case, because there is, in this case, there is no reason to do anything else. Let's call both these densities N, and let's call them This is called the initial density, N0 divided by 2. Then well, let me actually do it this way. To follow the same notation of the reference I'm using, I'm going to call this N0 minus N, where N is the reaction rate. The reaction rate is going to depend on time, as each reaction that occurs is going to reduce the number of available fuel ions, and therefore the number of deuterium and tritium ions is going to decrease as the reaction rate. And the burn fraction is going to be just the total number of reactions that happen over the experiment, divided by the initial density. So as a function of time, the burn fraction F sub B is going to be equal to N over N dt, or N over N0, not N0, sorry. N0 divided by 2. And you can integrate this expression, assume that there is a finite amount of time over which we have fusion reactions. Let's call it the burn time. Burn time tau sub B. And then I'm going to assume that sigma V doesn't change. And that gives me a burn fraction. So let me write an intermediate step. FB divided by 1 minus FB is going to be equal to N0 tau B divided by 2 times sigma V. And then you approximate this tau B as R over 3C sound. Crank the numbers, and you find that the fractional burn is going to be given by rho R divided what happened here? Divided by rho r plus C sound over sigma v. Which you'll remember from previous lecture that this is often approximated just as 6 in grams over centimeters squared. And that's valid for certain temperatures that are relevant for ICF. The point being that it is a straightforward calculation to get this burn rate if we make simplifying assumptions, as is often the case in physics. Okay, there is so much more to discuss here, but I would like us to take a break here and talk about something else at this point. I should should mention a lot more things, but let me just say one more thing. That, in fact, once the fuel starts burning, the burn wave that propagates from the center of the target where the the burn starts occurring outward has a stabilizing effect on the instabilities we did not discuss, but that I've mentioned multiple times that are an issue for ICF. So that once you get there, that's actually going to help you to get better and better. Okay, I wish we had 20 more lectures to actually do this a lot more carefully, a lot more in detail. I hope I've given you a reasonable idea. I hope that after these lectures, you'll feel you know more than you did before about ICF. If not, I'll recommend a reference. Okay, but now I want to actually stick to the topic, but move to a slightly different area. That is NIF experiments. Now, NIF is pretty expensive experiment. It contains 192 lasers. It's designed to do a lot of things, but for the ICF field, it's designed to achieve ignition that is net energy production in the indirect drive configuration. It's got a total laser energy that's of the order of 2 megajoules. I should write that down. And it was actually designed to reach ignition, and the first ignition campaign was more than 10 years ago. Things did not go as planned, and I'm going to follow a short summary from a paper that I will reference in the notes and on Canvas about what is happening, or what happened rather, and how did we get to the ignition shots in December 2022. Well, the one really good shot, but I will tell you in a moment that that's not as bad as it's not just a single event, it's not a fluke. Okay, so what is important to realize looking at ICF is that an easy metric to decide how well an experiment is doing or did, how well a shot did, is the fusion gain, which we have already encountered and defined as energy out over energy in. So of course, we want this to be bigger than 1. If it's 0.1, we only got 10% out of what we put in. We didn't do that much fusion. If we got 0.1%, that's even worse. One subtlety that you have to be careful about is that this is not a great metric. The problem is that it's not that obvious how to make a better one. But the reason why it is not a great metric is that the achievement of ignition is akin to an instability. It's a thermal instability. So ideally, you start having fusion particles, fusion products heat the plasma and get more fuel in the condition to get more fusion, and that burn wave propagates until you don't have any fuel left. That means that in numerical terms, if you were doing a numerical calculation, this would be a typical example of an ill-posed problem. Not because it's conceptually wrong, that's not what ill-posed means in this case, but because small changes in the situation, in the conditions, in the initial conditions, or in something else that happens during the shot will create big changes in the actual output. And in ICF, people talk about the ignition cliff. That is, when you get close to ignition, every little tiny step you make is going to make the gain quite a bit larger. You can make very small adjustments and go from 10% to 100%. It was a lot harder to get to that 10% than it's going to be to go from 10% to 100% or more. For the ones of you that are in magnetic fusion, you may want to look at papers describing burning plasmas. These plasmas where a lot of the heating is coming from alpha particles in magnetic fusion, and you'll see the modified Lawson criterion where you have also the input power. That's the difference between ignition where the input power is turned off and a burning plasma where you still need to feed some power into the plasma to get more power out. And you'll see that the Lawson curves get very close to each other when you get above Q equal 1, the break even. So the situation is quite similar. It's a lot harder to get to break even Q equal 1 than it's going to be to get from Q equal 1 to Q equal 40. Same in ICF. It's a lot harder to get close to ignition that actually do obtain ignition. Okay, the first ignition campaign was maybe it's going to be national ignition. From 2009 to 2012, and the idea and the expectation was to achieve ignition by 2012. It didn't happen. Here we had a very cold target, and we call this close to Fermi degeneracy. Unfortunately, what was found is that this made the fuel very susceptible to instabilities. So that means the this beta F equal to 1 will mean that you're fully degenerate state. So here, the input power was 1.8 megajoules, and the output power was a few kilojoules. So that's bad. It's less than 1%. In fact, even though in theory, in the ideal case, you will want to be as close as possible to Fermi degeneracy, so have beta F as small as possible, it turned out that just increasing beta F to, what was the number, or 2.5, quite increase the output, got it close to 25 kilojoules. Okay, so that's in the right direction, but it's still a long way to go. The next step, well, so the first step was to realize we really need to relax that requirement. That's going to requirement on beta F, which is again how close we get to fully degenerate electron plasma and electron fluid in the plasma. And the next step was to change what we've been calling the foil, that is the ablator material. That was done a little later. This is not random. It's actually there is quite significant. Oops. Let me pull this up a little bit. Work that gets into each one of these steps. I mean, why didn't people think of having high density carbon ablator before, and they used this other ablator? Well, because you had to design the material. Carbon. High density carbon. Once it was realized, if we can design this material, it's going to be more dense than the original one. Therefore, we can go to a higher aspect ratio, and we can also shorten the laser pulse and modify the whole round. Remember the cylinder the target is embedded into, and things are going to get better. And in fact, they did. To by about a factor of 2. Well, that's great. Still a long way to go. One, well, we have not discussed a lot of things, so I can only give you the very hand wavy discussion. But one additional step that was taken was to do what everybody's always known was a good idea, that is to make the target bigger, because we know the yield will scale with the size of the target. If we make it bigger, we'll get higher yield. Catch there is, if we make it bigger, we need also a bigger laser, and we don't have one. So the step in the optimization process there was to make a smaller hole around. If you do that, you need less laser energy to produce the same amount of X-rays. Or in this case, with the same amount of laser energy, you can make more X-rays and therefore drive a bigger capsule. But you've changed the geometry of your system. That means you have to do more experiments to redesign the shape and duration of the laser pulses and so on. So that was done in a series of campaigns starting from 2018. The other advances that were important in achieving ignition were an improvement in the HDC, high density carbon material. Again, it's not as simple as it may sound from this discussion. You want a specific material with some certain properties, you have to design it and you have to manufacture it. And it's not a matter of going to the supermarket and buying it. You have to invent it. And also some improvement in the target design, the rest of the capsule where the fuel goes, where those were the improvements that the modifications that led to an improvement in performance. And in fact, in these campaigns, the energy output was on the order 160, 170 kilojoules, which is still, we're still using 1.8 megajoules pretty much for our driver. So that's barely 10%. Remember what I said at the beginning, it's going to be a lot harder to get from 0.1% to 10% than it's going to be to get from 10% to 100%. And in fact, these shots were already made people very happy. We were getting burning plasma. What burning plasma means in ICF terms is that a significant fraction, in fact, most of the energy that gets deposited in the fuel is coming from alpha heating, about 2/3 of it, actually. So that means that the hotspot is self-heating. At this point, you haven't quite made the headlines of the newspapers, but you're pretty confident that you're going to get there. Just have to do some additional small refinements and adjustments, and you're going to go from 10% to much higher numbers. In fact, there's more than one, but using an expression, a modified Lawson criterion that applies to ICF, it was calculated that these shots got to between 75 and 85% of the requirement and the Lawson threshold for ignition, even though the yield is less than 10%. That is, again, to emphasize the point that it's not just the yield, it's how close you are to the ignition threshold. And that arguably could be a better metric than the yield, but yield is easy to understand. That's why it's used more. Okay, then what was finally done, the last shots, and actually the the ignition criterion was exceeded in a shot. I just had to pause to look it up. And that was in August 2021. And that is not the one that made the headlines. The output was still, the yield was still less than 1. The output was 1.37 megajoules. Again, remember what I mentioned earlier. At this point, you're done. You repeat the shot. You go back to, you don't go back to the drawing board. You pull out your finer tools to just make tiny, imperceptible improvements, and you're going to get ignition. That's what happened. In fact, since this experimental point is in a region where small changes can cause in the experiment can cause big changes in the actual yield. The first shots that were done to replicate this shot actually had a quite rather lower yield and output energy in the hundreds of kilojoules. Then with some additional small refinements, we got to the word headline Nobel Prize candidate shot. They don't give Nobel Prizes to shots or experiments, and I don't know if this is going to be considered, but it certainly made big news. And in that case, the yield was above 1. And I forgot to look up the number for this lecture. I'll try to find it and put it in the notes. Okay, so that's the story. What I want to leave you with is a reminder that this is a very complicated process. We had to learn a lot of physics and a lot of engineering to make this happen. Well, not with them, because I didn't do anything. I don't know about you, but a lot needed to be learned to make this happen. And once you start getting close enough from the 2020 campaign, you know you're going to get there. That's even if journalists will not be knocking on your door, and the public may not be interested, you know you're going to get ignition. Hopefully we'll do the same thing with tokamaks, and hopefully will take us a little less once our magnetic confinement experiments get online. They'll be able to perform as intended by design pretty quickly. They will not have to wait too long. Okay, I am going to close here, and hopefully I also made you curious about ICF, and we will move to rather different but relevant actually to ICF topic, starting with the next lecture. Thank you for your attention, and we'll see you for lecture 18.